Hello friends, welcome to the lecture series on design and analysis of algorithms. This is Sahil Shah from Baramati presenting lecture series on design and analysis of algorithms. We were discussing asymptotic notations. In continuation with the same, let's have a recap of whatever we have seen so far. In the last lecture we had a discussion on order of growth for a function, how to have asymptotic notations for algorithmic representations. We have seen what we mean by big O notation, then we have discussed big omega notation as well. The third type of asymptotic notation is big theta notation. What this is, big theta notation defines the tight bound for the algorithm. It means running time of any algorithm cannot be less than or greater than its asymptotic tight bound for any random sequence of data, which means running time of a specific algorithm with a function f of n will always lie between c1 g of n and c2 g of n for values of n greater than equal to n0. The theta notation is denoted using symbol f of n is equal to theta g of n, where g of n is equal to f of n. We have seen in case of big O notation, f of n was lower than c1 g of n, while f of n was greater than c1 g of n in case of omega notation. In case of theta notation, it must be equal with g of n. The graphical representation of theta notation is given by this graph. We can observe f of n is lying in between c1 g of n and c2 g of n. At max, f of n will be equal to g of n. After a particular point n0, crossover point n0, f of n value will not go more than c2 g of n, or it will not go down below c1 g of n. As theta notation is mainly used to denote average case time complexity of any algorithm, it doesn't have any loose bound because it makes use of equal to notation. Let's have an example. If we want to find maximum number from a list of integers, we can probably go through all the possible integers and check out which one is maximum. The next possible choice is the maximum element is present at the first place. What are the average number of comparisons required? On an average, I will require n comparisons. So theta of n is the average case time complexity for finding out maximum number in an array of integers. Loose bound does not exist for theta notation, while incorrect bound exists. What is incorrect bound in the case of theta notation? All the set of functions with the growth rate lower or greater than its actual bound are said to be incorrect bounds for that function. Example, let f of n is equal to 6n plus 5, then it is equal to theta of n. So that is correct, theta of n. While if I say it is equal to theta of 1 or theta of n square, theta of n cube, all these are incorrect. For 3n cube plus 5, it is equal to theta of n cube, while it is not equal to theta of n square, neither it is equal to theta of 1, neither it is equal to greater theta of 2 raised to n or theta of n factorial, and so on. The next sort of asymptotic notation is little o. Big O notation was giving us tight bound or the bound which may not be tight, but in case of little o notation, it is used to denote a bound which is asymptotically not tight. In case of big O notation, we were having an equation 0 less than equal to f of n less than equal to c into g of n. Okay, so that equal to, less than equal to was contributing in giving us the tight bound. If we are interested in all those bounds which may not be tight, then this little o notation is used. Example, 3n square belongs to little o of n cube, but 3n square will not belong to little o of n square. N square, there is a match, and we are interested in all greater bounds. There should not be equality. So this little o, small o of g is lesser than big O of g. Big O of g will have more number of functions comprised irrespective of little o. Correct bounds, if I say 6n plus 5, what is the correct little o bound? It will be little o of n square. In case of big O, I could have probably written big O of n, which was correct here. Big O of n will not be correct. Little o of n will not be correct. Little o of n square, you need to have something higher, not equal. 3n cube plus 5 will not be equal to little o of n cube, while it will be equal to or belonging to little o of 2 raised to n, little o of n factorial, and so on. Moving further, little omega notation. This is totally opposite of little o notation. It is used to define a bound which is asymptotically not typed. So example, 3n square can belong to a little omega of n, but I may not say 3n square is equal to little omega of n square. That is totally wrong. So small change in the function. Here we were writing less than equal to f of n. In case of big omega notation, here we are writing 0 less than equal to c g of n, which is less than, strictly less than f of n for all n greater than equal to n0. And we can deduce this little omega of g will always be greater than big omega of g. It will have greater number of terms involved. Let's see correct bound for 6n plus 5. Correct bound omega 1 will be correct, while omega of n will not be correct. 3n cube plus 5, omega of n square will be correct, lower, but omega of n cube is not correct. Okay, so what are the properties of all these asymptotic notations? The first property of asymptotic notation, known as correlation. What it says, f of n is equal to big O g of n. This indicates that f is always lesser than equal to g. If I say f of n is equal to small o, little o of g of n, then f will be strictly lesser than g. In case of f of n equal with theta of g of n, f tends to be equal with g. If I say f of n is equal to omega g of n, then f is greater than equal to g. If I say f of n is equal to small omega g of n, then f must be strictly greater than g. The second property of asymptotic notation, reflexivity. F of n is equal to, this function f of n can be represented in terms of theta, big omega, big O notations with itself. F of n is equal to theta f of n, that is equal to big O f of n, which is equal to omega f of n. Let's take an example. Let f of n is equal to 3n plus 5. So what is the lowest possible upper bound for 3n plus 5? n itself. So I can say 3n plus 5 a function is equal to big O of n, that is equal to lowest possible lower bound, greatest possible lower bound 3n. So I will say omega of n, which is equal to theta of n, a function represented in terms of theta, big O and big omega notation, reflexivity. Third property, symmetry. If we are having two functions fn and gn related using theta notation in the manner f of n is equal to theta g of n, it can exist if and only if g of n is equal to theta f of n. That means if fn is equal to gn, gn has to be equal with f of n. The fourth property, transitivity. If we are having three functions f of n, g of n, h of n having relations, f of n is equal to big O of g of n, g of n is equal to big O of h of n, then I can deduce a relationship in between f of n and h of n as f of n is equal to big O of h of n. Same property will hold true for omega and theta notations. Always try to remember, if we write f of n is equal to big O g of n, then g of n will act as an upper bound. It will have higher or equal time complexity as that of f of n. Getting? The fifth property of asymptotic notation, transpose property. If we are writing f of n as big O g of n, then reverse is also true. That means g of n will act as sorry, f of n will act as a lower bound for g of n. How to read it? G of n is a upper bound of f of n. That means f of n is a lower bound of g of n. How lower bound is given? Lower bound is given by omega notation, while upper bound is given by big O notation. If I write f of n is equal to big omega of g of n, at the same time I can say g of n is equal to big O f of n. Same will hold true for little o notations as well. If we say f of n is equal to small o g of n, this can happen if and only if g of n is equal to little omega of f of n. So converse is always true. Manipulation. The sixth and final property: if some constant is multiplied with big O of f of n, the result will be big O of f of n. As we already said, seen constants will be treated as minors and those can be simply reduced to major terms. If I have big O of f of n, it will be nothing other than big O of f of n. In case of normal multiplication of two time complexity values, big O of f of n multiplied by big O of g of n, this can be given as big O of f of n multiplied by g of n. In case of addition, big O of f of n plus g of n is equal to big O of maximum amongst f of n comma g of n. The interested users are advised to pause at intermittent stages and try these properties with the sample examples for better understanding. So there are 6 prominent properties of an asymptotic notation, starting from correlation, where a one-to-one correspondence between f and g is represented based on big O, theta and omega notations. If we are using big O, it will be less than equal to. For small o, it will be strictly less than. For big omega, greater than equal to. For small omega, strictly greater than. For theta notation, there will be equality. Reflexivity, representing a function with itself. So function can be represented as its theta, omega or big O counterpart. Symmetry, if a function has average case time complexity of g of n, then g of n must have average case time complexity of f of n. Transitivity, if there are 3 functions where f is dependent on gn, gn is dependent on hn, then fn will have a dependency on h of n. Transpose symmetry, counterparts of respective terms. If I say f of n is equal to big O of g of n, I will say that g of n will always have a lower bound of f of n and so on. The final property that we have seen is manipulation, where there is a rearrangement of terms. In case of constant, that can be simply neglected. If we are having double or triple big O usage, we can simply reduce it to single big O notation. Value will remain one and the same. In case of normal multiplication, a multiplication of individual functions can happen and the final multiplication can be equal to its upper bound, that is big O of f of n multiplied by big O of g of n. The final, if in case of addition of 2 functions, what shall be the upper bound? Upper bound will always be maximum in between 2 functions. Let's see the example. Find the upper bound for running time of linear function f of n equal to 6n plus 3. As we know, what is the formula for computing upper bound? We are having a mathematical notation: 0 less than equal to f of n less than equal to c into g of n for all n greater than equal to n0. Let's put our function f of n here. 0 less than equal to 6n plus 3 less than equal to cgn. Our goal is finding this value of cgn. How to find this? I know that 6n plus 3 will be lesser than. We need to simply copy paste all these values and append all the constants with the highest polynomial terms. So in this equation, 6n plus 3, n is the highest, so I will say 6n plus 3 is less than equal to 6n plus 3, 3 is appended multiplied with n, 6n plus 3n for all values of n greater than equal to 1. 6n plus 3n becomes 9n. Okay, so if we compare 9n with cg of n, I will say that value of C is 9, G of n is n, and value of n0 is 1. This is the way by which upper bounds can be computed. What to do? Write the formula for upper bound 0 less than equal to f of n less than equal to C G of n, and then we are replacing the terms by highest polynomial in the given function 6n plus 3. So C of G of n, we are writing 6n plus 3 will always be lesser than equal to 6n plus 3n. So I am arriving at a conclusion 9n. So I am getting a value of C as 9, G of n as n, and n0 as 1. Let's try second example. 3n square plus 2n plus 4. So our formula is 0 less than equal to f of n less than equal to C G of n. So put those terms C G of n. Here n square is higher, so I will first copy down this 3n square plus 2n square plus 4n square that we have written. You can observe. Okay. Now what is the conclusion? This is again coming 9. C will be 9. Compare this 9n square with this C G n. C is 9. G of n is n square. We get the value of n0 and so on. This is with respect to finding upper bound for given function f of n. What changes are required if I am interested in finding lower bound? So I will simply replace this. Here we were writing fn here. Now this C of gn will come here, f of n will go here. So we will have for lower bound, I will say 0 less than equal to C gn less than equal to 6n plus 3. 6n plus 3 will be lesser than 6. We now are interested in lower terms. 6 plus 3, that will be 9. 9 less than equal to 6n, yes, 9 into 1. So we will have constant C as 9, G of n as 1 in case of lower bound. Users are advised to use the functions and notions seen so far in order to know the correct results. I mean to say, if we are writing like this, 0 less than equal to f of n less than equal to C into G of n. I hope you are understanding. Let me have bigger font with size more so that you will have clear understanding. I hope now this is visible. This is for upper bound. If I say 0 less than equal to C G of n less than equal to f of n, this will be lower bound. And if I say C1 Gn lesser than equal to f of n, this is less than equal to C2 Gn, this will be equal oblique theta oblique tightest possible bound. Okay. Remember here it is 0 less than equal to. Okay. Now the things are clear. Example, let us say we have been given f of n is equal to 5n plus 3. So question, what is the upper bound for f of n equal to 5n plus 3? Also they will ask you what is the worst case time complexity for f of n equal to 5n plus 3. So you can use this formula. Formula number 1 for upper bound, 0 less than equal to. So instead of f of n, I will write my function 5n plus 3. This should be less than equal to C into G of n. That is what known to us. How to solve it further? On the next line, 0 less than equal to 5n plus 3. This should be less than equal to, suggestion here, write the entire equation as it is, build the highest terms and so here I am observing that n is the highest, 3 is a constant, so I have copied first 5n plus 3 here, 5n plus 3, and 3 is appended with n. So at the end I am getting a result as 0 less than equal to 5n plus 3, it is less than equal to 8n. That means what? Worst case time complexity of a column or function f of n 5n is n, 8n. You can represent it like this. Okay. For lower bound, what to do? Okay. For lower bound, we will have this formula simply revised. So I will say 0 less than equal to c g of n less than equal to 5n plus 3, that is our function. Okay. Now what we will be finding out, copying it down. Copy all these terms 5n plus 3. Now at the time of copy, we will be multiplying every constant with lowest possible digit. So here you will say 5 and plus 5 plus 3. This will be less than equal to 5n plus 3. Now again a question will come, why I have written 5 plus 3? Because 5n, n is one polynomial term, 3 is associated with a constant is lesser than this n, so we have taken 5 plus 3, 8. So finally we arrive at the conclusion 0 less than equal to 8 less than equal to 5n plus 3. Okay, this will be lower bound for a function 5n plus 3. What it will be? It will be a constant time 8. It's a constant. Remember the example of finding out maximum of a number. Now, how about equality? Okay, what is our equation? Equality 0 less than equal to c1 gn less than equal to f of n less than equal to c2 g of n. So simply we will replace c1 g of n, c1, okay, f of n is more, so here I will write 5 plus 3 less than equal to 5n plus 3 less than equal to 5n plus 3n. I hope your thinking is correct. So meaning is it will be less than equal to 5n plus 3. This is less than equal to 8n. So I have reduced the tight bound as n in this case. Okay, this will give us the average case time complexity. Okay, based on this, users are advised to solve this problem, a practice problem asked in mid 2017 university examination. Calculate best case, average case and worst case time complexity of following functions. We have been given two functions. F of n is equal to 3n n square minus n plus 2n plus 5. Second, f of n is equal to 4n cube minus 15n square plus 30n equal to 25. Using instead of this equal to, consider minus 30n minus 25. There is a mistake. Should consider minus 25 using running time complexity. So for first example, we are observing the highest polynomial term is n cube. So worst case time complexity will not exceed n cube, while the lowest time complexity will be a constant time. Users are advised to check the previous example for solving. In case of doubts, you are always free to ask. Feel free to contact me. Wish you all the best. Enjoy learning. Happy learning. Stay safe. Stay healthy. Thank you.